then their clocks appear to go slower. Or more precisely, if you went off in a spaceship at very, very high speed for long enough and came back again, you would come back and find that you were a bit younger than the people who'd stayed here. Yeah. Now, let me give you a specific example of that. Cosmic rays, high in the atmosphere, come flying in, and there are nuclear reactions occur high in the atmosphere. There are particles produced which have a very short lifetime. They decay in, shall we say, a microsecond. Such a short lifetime that even if they went at the speed of light, they wouldn't get here. Do you follow me? If light goes at 1 foot in a nanosecond, it goes 1,000 feet in a microsecond, it's not going to get from the top of the atmosphere down here in a microsecond. But they get through. Why do they get through? Because they're going so fast that their time slows down. That makes sense? So it is specifically and experimentally true, and certainly true in these sort of experiments in CERN, that you can experimentally measure the fact that something that's going very, very fast, its time slows down. Now, what's the question again? Have I answered it or not?
No. I must confess I don't understand it. I've read Brian Cox's, or tried to read Brian Cox's book, E equals mc squared, or Y does it? And he gives an explanation of using the train, someone in the train with 2 mirrors, I think, a metre apart, and the light bounces between the two. Yeah. And this train is travelling almost at the speed of light. And to the observer, he's trying to explain that.
Right. I mean, it is very counterintuitive. Yeah. But I mean, the experimental fact is that if you are going very, very fast and you measure the speed of light, it is still the same. And it's the extraordinary thing that, you know, the Earth is going around the sun quite fast. But if you measure the speed of starlight coming towards you and the speed of starlight going, you know, coming in the opposite direction, they're the same. Okay? Now that is very counterintuitive. How can the speed of light be the same? Because, I mean, you know, if you're going through air, the speed of sound coming towards you is certainly increased, and the speed of sound going away from you is certainly increased. So it's very, very counterintuitive, but experimentally it's a fact that the speed of light does not depend on your speed. Now, when you put that together, you find you've got to... The technical term is the relativity of simultaneity, which means you and I may think that 2 things happen at the same time. But someone who is moving at a considerable speed will say, no, they didn't, that happened before that. And we're both right. It's what, I mean, relativity is hard to understand, it's not trivial, but it's well understood and well supported experimentally. And particularly, I mean, for things like CERN and the Large Hadron Collider, it's part of the engineering. In other words, there are engineers there who are belting particles around at such a high speed that they have to use the equations of relativity to get it right, otherwise they get it wrong. So it's not a high-flown, fancy theoretical thing with no practical knowledge. You've got to use the equations to get the right answer. I think I worn you all out. It's 9 o'clock. Should we call it a day?
Thank you very much.